Okay, class. I've been looking over this here for a while and doing some other stuff, but it's time to do another lecture. I always think about, what's the best way to put the lecture together, because there's usually 3 or 4 different parts to a lecture. They all mean something and they're connected in some symbiotic way, but if you don't do them in the correct order, sometimes it doesn't get across. Now, what we're going to talk about today is capacitive energy. And I'm actually going to do a problem too. We're going to sort of look at a design of a system that would solve a problem for our moon base, right? Anyway, let's go on. The first thing that I want to do is I want to just look at capacitive energy. And if we think about work, let's say that work, as far as electrical, work goes, that's voltage times charge, right? And so if we have a small amount of work, dW, then that would be voltage times a small amount of charge, right? And I always like to say, hey, what are the units of volts? That's kilogram meters squared per seconds cubed amps, and charge is an amp second. And so we know that that going together equals a kilogram meters squared per second squared, doesn't it? Always think about, always think about what it is that you've got here, right? Work kilogram meters squared per second squared. Voltage kilogram meters squared over seconds cubed amp times an amp second, right? So it all cancels out. It all works out fine. I just always like to throw that in there. And we know that V equals Q divided by C, right? I'm just using that small q because I'm going to be using dq in a second. I made the q and the dq small, so basically what we have is that that small amount of work, dw, is going to be q over c times dq, right? So if I wanted to find out what the total work was, I would just integrate over that small amount of work, dw, or from 0 to q of q over c times dq, which gives me 1 over c times the integral of 0 to q of q dq, right, which is a pretty easy integral to figure out, or w equals q squared over 2c, right? So w equals q squared over 2c. That's one way that we could look at w, but we know that v equals q over c, right? We say that all the time. V equals q over c, v equals q over c. Look, I've said it right up there, right above that. Wow, I can't write it down enough. So that tells me that v squared equals q squared over c squared, doesn't it? Or q squared equals c squared times v squared. So if I can replace q squared with c squared times v squared and then cancel out one of those c's with the one on the bottom, That gives us our well-known equation, omega equals V squared times C over 2, right? CV squared over 2, capacitive energy, right? So that's another great one. But again, V equals Q over C, doesn't it? Or Q equals CV. So W also equals Q times V over 2, right? Now let's extrapolate that a little more because we want to look at that work. And we looked at this a little bit earlier, but more from a point of the definition of capacitance rather than definition of capacitive work. And I just wanted to sort of point this out. So the work that we've got, or the energy in a capacitor, is going to be equal to, and let's replace a couple of these things, right? Because we've got a couple of these. So we know that V equals E times D, right? The thickness, D being the thickness of the capacitor. So D equals thickness. And of course, the thickness times the cross-sectional area gives me the volume, but let's just look at this first. And you know, what's Q? Isn't Q equal to the flux times the cross-sectional area, the flux density, I should say, times the cross-sectional area? In fact, isn't that the definition of the flux density, is the charge divided by the cross-sectional area, right? So Q equals dA, but what does D equal? Doesn't D equal epsilon times E times A, right? So if I really look at the work here and I replace Q and V, then what I end up getting is I get epsilon E times A, right? That's Q. And then for V, I get E times D, the thickness. And then the bottoms, I still have 2. So that says that that's epsilon E squared times AD. And I like to put a parentheses around AD because, of course, that is the volume, isn't it? And let's not forget over 2. Because that's the volume. And of course, when we look for the specific work or energy density, right? It's called the specific work or the energy. I'm just trying to give you some of the terminology that is used in our profession so that when people start mentioning it later on, you'll know what they're talking about. And of course, that's per volume, right? The energy density, the specific work, and that would be this divided by volume. And what is that? That is volume. So that's just going to be epsilon. And let's not forget that epsilon equals epsilon sub r times epsilon sub L, right? So epsilon times E squared over 2. All right. That's my specific work. Now, what I want to do, and yes, I did put my timer on. What I want to do, let's just break this section of the thing off here. Just go up here, cut across there, come down here. Hey, why am I doing that? Why don't I just go across here? What the hell? Sorry about that. Anyway, I need, there we go. So I'll just use my correct type here. There we go. I find this better than the old tape correct type, which I think I ran out of anyway because I can't find it anywhere. Um, so when we do that, and that comes back to the same point that we had the last time when we were working on, when we looked at the lecture that compared the mica to the ceramic capacitor, right? And I want to go back and just look at that for a second because I want to do a example problem that's very similar to that, but is a little more interesting. So when we went back and we looked at the mica and everything else, let me just sort of recap what we had. For mica, we had the relative permittivity is 5, but the maximum dielectric breakdown strength that it could have as far as maximum electric field was 196.5 times 10 to the 6 volts per meter, if you remember. On the other one, we had the relative permittivity of strontium titanate, and that was 7,500, but the maximum field that it could have was just a minuscule 2.95 times 10 to the 6, which, by the way, is comparable to air, right? Comparable to air. So it's not very high whatsoever. That's the problem, or we would be making all of our capacitors out of strontium titanate. Right now, we make the smallest button signal capacitors that don't have very large electric voltages across those capacitors. So you can use those, but you can only use those for the smallest, like, signal. You can't use them for big power ones, but I want to look at an example where we would use those for large power capacitors. Now, let me go on. So that was the thing, and when we talked about the givens, the characteristics of the problem, we found out that the voltage across that capacitor was going to be 600 volts, and we wanted the capacitance to be 1 farad. And what that meant was that the energy, and I want to write out energy because, you know, we're using E a lot for electric field. I don't want anyone to think that I'm also, you know, talking about electric field here, so I'm going to write out energy. When we're talking about the energy that was inside that, of course, that was going to be CV squared over 2. And when we multiplied that out, that came out to 180,000 joules. I'm not going to go through the solution of the problem. I'm just restating the results that we got out of the problem. And really what I want to do is really focus more on the ceramic than on the mica. And so what we found for a minimum distance for the ceramic was 203 microns thickness, you know, relatively thin thing, except that the mica was only 3 microns. And then the cross-sectional area that we got for that was 3,058 square meters, which gave us a total volume for the entire endeavor of 0.621 cubic meters. And when you think of something that's 0.621 cubic meters, you would think of something that's about 0.85 meters on each side. So really think of something that's probably a meter by a meter by a meter, 1 meter. And that's, and I'm making it look like this on purpose, but that 1 meter, 1 meter by 1 meter gives us 180,000 joules of stored energy that we can use. Stored energy. That's what I want you to think of. Now, that is exactly the same amount of energy that I want to put into another capacitor that also is going to be about the same volume, because that's another thing that we learned about the energy for the energy per unit volume for the ceramic, right? These are all, by the way, for the ceramic, not the mica, but the ceramic material, strontium titanate, barium titanate, strontium barium titanate, whatever, that we use in small signal capacitors. So that was what the volume we got. This was not as good as the mica for storing energy as far as energy density goes. And this is one thing that I do want to write down, is when we looked at the energy density. Oh my God, look at that. I've got energy density written right above where I'm going to write the energy density down, almost like I planned it. Anyway, when we look at the energy density of ceramic, right, so energy per unit volume, I'm going to put N for energy. That is, of course, 1/2 epsilon squared. I'm not even going to write that down because we're going to look at the two of them. So first of all, for the ceramic, and I'm going to write the whole word ceramic out there, it was 288,814 joules. And I'm not sure I even gave you this, joules per cubic meters, but I'm not going back to actually check that. So that was for the ceramic, right? That was the energy density, joules per cubic millimeter, or specific work if you wanted to look at it that way. The energy per unit volume for the mica, and this was where we all realized, oh, hey, you know, 7,500, that's not the thing that entirely matters. The breakdown strength matters too, and it's got to be a fine dance between those two. So when we looked at the mica, we found the energy density was 857,342 joules per cubic meter, right? So that's what we found for mica. We also found what the charge was. I could write that down. I'm just going to compartmentalize this a little bit. The charge we found on that was 600 coulombs, right? And again, we go back to these equations we've got up here, V squared C, Q, V, everything else. So we found out that that was also 600 coulombs. What else can I give you here? That I think that was about it. Anyway, that's not what I just wanted to give you that information so that we could sort of compare these for this problem that I want to do. And there it is. All right, now let me just, I'm gonna cut this section off. Look at this, I'll do a double line. There we go. And do I still have plenty of time for this? Oh yes, I'm even timing now. Yep, I've got plenty of time to do this example problems too. So what I wanted to look at was, what if I changed this? What if I kept it the same amount of energy, right? So the energy per this capacitor that I'm going to design is 180,000 joules. All right. But instead of making it 600 volts and 1 farad, I want to make it 60,000 volts, because I can work with that type of voltage on the moon. And I want to make it 100 microfarads, right? I also have to make it out of rare earths, because on the moon I don't have any mica. And the soil, the moon soil itself, is rich in rare earths that I can you know, make that type of ceramic type of dielectric out of, but I can't really get anything else. There's no glass. I can't really make it out of anything else, but I can make it out of this. And so my relative permittivity then is going to be my 7,500, and my my breakdown strength, and too bad we don't have a common symbol for dielectric breakdown strength, but I don't mind writing it out. So the dielectric, sometimes they call it dielectric strength. Yeah, I guess I do mind writing it out. Is 3 times 10 to the 6 volts per meter, right? I said it was 2.95, but I'm going to round that off to 3 times 10 to the 6 volts per meter. And so anyway, the first thing that I want to do to figure this out is what is the minimum thickness of this capacitor that I could make, and that's going to be 60,000 volts divided by 2.95 times 10 to the 6 volts per meter, right? And that gives me 20.34 millimeters. 20.34 millimeters, or 0.02034 meters, right? So anyway, we just have it there, and of course you know how to punch it into your calculator and everything else. Now, what would the cross-sectional area be? So my cross-sectional area is going to be equal to my capacitance times the thickness that I've got divided by the permittivity of the material, right? So let's see, C is going to be 100 microfarads, and I take it that everybody knows how to punch that into your calculator. And then D is going to be 0.02034 meters. And then epsilon is going to be 7,500. Now, if you stopped there, oh my God, I just wrote it up here. Epsilon equals epsilon sub r times epsilon sub O. That's right. Don't forget it. And so there you go. That's our cross-sectional, that's our equation for our cross-sectional area. And that comes out to be 30.64 square meters. And you know, you're saying to yourself, oh my God, look at that. It's 30.64 square meters when he ran it up to 60,000 volts. And when it was 600 volts back here, the area was 3,000. It was literally 10 times as high here. Oh my God. Yeah, but look at what this was, right? Instead of this being 20 millimeters, this was 203 microns, right? So there's a big difference. Of course, it's a big difference. And of course, the volume here is going to be exactly the same as the volume here, isn't it? Because the energy is the same. And we know what the energy per unit volume is. So if I multiplied 30.62 times 20.32, I would get a volume. Let me just do that. A volume equals 20.34 millimeters. I'm going to let you guys change that into meters times 30.64 square meters, and that's going to give me 0.621 cubic meters, right? So we know that, and we know that it's 180,000 joules, and that's going to be the same, and it's the same energy density. So it's sort of a check. It's sort of a check of your math to make sure that you've done everything okay. All right, now we've done all of that. Now we can make these on the moon. They'd be about a meter by a meter by a meter. In fact, they'd be 0.85 meters by 0.85 meters by 0.85 meter cubes. Each one would contain 180,000 joules of stored energy, right? Now, What if we made a mass transfer device on the moon, and we had to power that so that it could take both human cargo as well as ore cargo back from the moon and send it not only to Earth, but to send it to other places too, right? Send it like it's a shipping thing. It just fires it off there. And what we're going to do is we're going to want it to get to 6,000 meters per second. So our final velocity is going to be 6,000. And I'm saying a maximum because we don't need 6,000 meters per second for the trans-Earth injection velocity, do we? No, everybody knows that we only need about 3,100 meters per second for that, don't we? But from the moon trans-Mars injection, we need about 4,300 at maximum, right? I know. What do you guys do with your time? But almost every place that we would want to go in the solar system, we could launch probes off the moon for electrical energy that is about 1/1,000,000th the cost that we are currently launching things into the outer solar system from the Earth, right? Because we can make a mass transfer device where we just accelerate it up to moon escape velocity, which is 2,380 meters per second. And, then we'll probably need an extra 1,000 or a couple thousand to get to Mars, an extra 1,000 to get back down to Earth. If we wanted to go out and send probes out to Jupiter or Saturn, that's where we'd be using the 6,000 meters per second, and we would never need another rocket. This is what people don't understand. Rockets are not the future. There's no rockets in the future. I mean, there are rockets in the farther future, but once we get to the moon and we start using the moon and we have a base on the moon, all of our stuff's going to be launched into the outer solar system from the moon, not from the Earth. And that's what we want to look at. So if we've got a final velocity of 6,000, we want to keep the G forces at 1G, right? So we want our acceleration to be 9.81 meters per second squared. That means that to get up to that velocity at that acceleration, 6,000 divided by 9.81, that time would be 611 seconds, right? So we've got something that's 611 seconds long, but we know that its final velocity is 6,000. So we know that the total energy that we need is going to be 1/2 mass times velocity squared, right? That's right. We need energy that's about mass, whatever the mass is, and what is the mass? The mass is going to be 1,000 kilograms. So that's about 2,200 pounds. Now, 2,200 pounds, that's about 10 people, maybe less people with other, amenities on board, but maybe 10 people, maybe 8 people, or 1,000 kilograms of ore that could be sent, or medical supplies, or whatever, to all of our bases throughout the solar system, right? And then we want to accelerate that to 6,000 meters per second, which could, and I say that is a maximum. That would be like sending it out to our Saturn or asteroid belt colonies, and getting it out there. It would take a long time, but UPS is so slow in the outer solar system. Divided by 2. I'm talking, like the pandemic's not going to kill us all. Anyway, I get 18 times 10 to the 9 joules, right? So how many of these individual capacitors are we going to need? So the number of capacitors we need is the number of is the amount of energy that it's going to take to launch this either human or cargo, divided by the number, but by the divided by the energy that we have per capacitor, which is 180,000 joules per capacitor, right? And of course, what that gives us is 100,000 capacitors. Now, can we make that on the moon? Sure, of course we can. And are we going to? No, probably not. We're probably going to bring a nuclear reactor to the moon and put it on the moon and do it with the nuclear reactor, of course. But if we wanted to, and we, this is the green colony on the moon. They decide, no nuclear reactor. We're just going to make capacitors out of moon dust, and we're going to use them to store up our own mass driver so that we can shoot it out to the outer solar system. All right. Well, yes, that's what I thought we should do. So you got 100,000 capacitors, and you've got that much energy. Here's what I want to look at. If we've got that much energy, how much would that cost us electricity-wise? Because joules and there's 3.6 times 10 to the 6 joules in 1 kilowatt hour. And I'll let you figure that out for yourself, because there's 1,000 watts in a kilowatt and there's 3,600 seconds in an hour. I'm not going to do it. You're seniors. I'm not going to do it for you anymore. I'm not going to. So let's get back to this. And how many kilowatt hours would that be? Well, I'll tell you what. That would be 5,000 kilowatt hours, right? Does everyone see that? 5,000 kilowatt hours, how much would 5,000 kilowatt hours cost me? And I'm just thinking 14 cents, maybe 15 cents a kilowatt hour, right? Did I get that wrong? I mean, nowadays, I'm just thinking of, let's see, 5,000 kilowatt hours times, I'm saying you could do it with solar on the moon. So I'm saying 15 cents a kilowatt hour. So 0.15. That's $750. So there you go. I just sent 1,000 kilograms out to Jupiter for $750. I know, and they're still taking it out of my paycheck that I hit the wrong button too soon. No, that's they would. So $750 in electricity, that's so minor, isn't it? And when I say 6,000 meters per second, what does 6,000 meters per second equal? 6,000 meters per second equals 21,600 kilometers per hour, right? So that's pretty good. That's about 12,000, 13,000 miles per hour. Even though it's a long way out there, that's quite fast. It's going to take a while to get to you, but it's still going to get to you, and it only costs $750. Now, Mom, I want you to send me that toboggan for the kids. We're out here in Jupiter on Europa, and we got ice and snow everywhere. And giant worms coming up from the bottom. No, that was the Europa report, a horrible movie. But that's what I'm saying. So they need to toboggan out there and some other things. And hey, Mom, send it. It's 1,000 kilograms. And so she has it fired off the moon. And before you know it, it's out on Europa. And human children 250 years from now are sledding all over Europa. That would be so good. Now, here's another thing. How fast have these things actually, 611 seconds, so we can actually get a power? And we've got to think about this, because can we discharge this much capacitance in this short a period of time, 611 seconds? And the answer is, yeah, absolutely. No problem with that whatsoever. So we've got 18 times 10 to the 9 joules. Oh, there's my timer. But I'm almost done. 18 times 10 to the 9 joules divided by 611 seconds. And that is 29.5 megawatts of power. Now, if there's 745 watts to a horsepower, right? So 745 watts to 1 horsepower, and we can think in horsepower maybe a little easier. That comes to 39,600 horsepower, right? Very small. I mean, it's not even a small ship as far as the power goes to launch things into space. Yeah, MIT students came up with this a long time ago, back in the 70s, I think it was originally. And it's a great idea. And of course, that is what the future of the moon and everything is to launch things further and further out into space, man the moon. We're not going to let anybody, any other men but Americans land on the moon, I'm sure. All right. Thank you for this lecture, and I am going to think about another lecture, and it'll probably be another 2 hours before I put one together, but I think this is a pretty good one, and I think it's the end of capacitors for us, too. We are now going to move on and start to talk about a variety of different transmission, metallic transmission media, right? Metallic and obviously dielectrics in there too. But that's what we're going to go into, and I'm trying to decide where we're going to. We may do a couple other interesting topics before we get there, but we'll see. Okay.